So now we are going to understand the importance of Gauss law. Okay. So according to Gauss law, the electric flux is equal to Q by epsilon naught. But we already know that the electric flux is also equal to E a cos theta. So these two formula are valid formula, but this formula is more complex as compared to this formula which is derived by the Gauss law. According to Gauss law, the electric flux only depends upon the charge enclosed by the surface, and it does not depends upon the shape or size of the surface. So here we try to calculate the electric flux in these three diagram by using Gauss law and also by using this formula. Okay, since the electric charge in this cross surface is 0, so the electric flux will be 0 according to Gauss law. But if you want to find the electric flux with the help of this formula, so in cylindrical surface, there are three types of surface here. This is cross-sectional area, this is cross-sectional area, and this is curve area. And here the angle between the surface direction and the electric field is 180 degree. And here the angle between direction of a surface and electric field is 0 degree. And here the angle between the direction of a surface and electric field is 90 degree. So the total electric flux will be phi 1 plus phi 2 plus phi 3. And if you sum these total electric flux, then you will get 0, because as we know that the angle of value of cos 180 is equal to -1. So this will be minus EA, and this will be plus EA, and this will be 0, because here cos 90 degree value is equal to 0. So when we add these phi 1, phi 2, phi 3, then we get 0 value. Okay, and since this is complex calculation, and if you use electric flux formula according to Gauss law, then you easily find out the electric flux will be 0. Okay, and in this condition, the electric flux is also 0, because the total charge enclosed in the surface is 0, because this charge is outside this surface. And if you want to find out the electric flux with the help of this formula, then you can consider that the total number of electric field lines enter this surface is equal to the total number of electric field lines leaving the surface. So the resultant electric field lines will be 0, and as a result the electric flux is 0. And in this situation, the electric flux only depends upon the charge enclosed by the surface, that is Q2 charge, and the electric flux will be Q2 by epsilon naught. Okay. So now we are going to discuss some application of Gauss law. With the help of Gauss law, we can find out the electric field, and if the charge are symmetrically distributed. And here we consider infinite long straight wire having uniformly charged. Okay, and we have to find out the electric field due to this long straight infinite charged wires. Okay, and here we are going to find out the electric field at a distance of r from these charged wires. And here you can see that the Gaussian surface due to this infinite long straight charged wires is cylindrical. And as also you can see that there are three types of surface formed here. This is cross-sectional area, and this is also cross-sectional area, and this is curved surface area of the cylinder. Okay, and here we consider a length L of the infinite long straight wires, and in this L length the total charge present is Q, and so the linear charge density will be lambda is equal to Q by L. Here lambda is the linear charge density. And if you want to find out the total flux through this Gaussian surface, then it will be phi 1 plus phi 2 plus phi 3, means the electric flux due to this surface area plus this surface area, and plus the electric flux due to this curved surface area. Okay, and here you see that the direction between electric field and the direction of surface is 90 degree, and also the direction of electric field and direction of a surface have angle 90 degree here also. But in this curved surface area, the direction of electric field and the direction of a surface curved surface area is the same, so the angle will be 0 degree. And as a result, the phi 1 will be 0, because as we know that the electric flux is equal to Es cos theta, and since here the angle is 90 degree, so cos 90 is equal to 0. So here Es cos 90 means this will be 0, and this is also 0, because here also we apply Es cos 90 degree, but here the angle is 0 degree, so the formula will be Es. S means surface area, but here this is curved surface area, so the formula will be 2 pi r h. The curved surface area of a cylinder is 2 pi r h, and here in place of h this is L, so we can use E into 2 pi r L cos 0 degree. Okay, and as a result we get a total flux is equal to E into 2 pi r L. Okay, and let's take it equation 1, and if we use Gauss law, then the total flux will be Q by epsilon naught, and here the LHS is same, so the from equation 1 and 2 we get E into 2 pi r is equal to Q by epsilon naught, and as a result we get E is equal to this 2 pi RL will be goes to denominator. Okay, and as a result we get 1 by 2 pi epsilon naught, and in place of q we can use lambda L. Okay, so we use lambda L, and this epsilon naught goes to here, and as a result we get this formula L to L will be cancelled out, and as a result we get E is equal to 1 by 2 pi epsilon naught lambda by R formula. Okay, and so we can say that the electric field due to infinite long straight charge wires at a distance of r will be 1 by 2 pi epsilon naught lambda by r. But since the electric field is a vector quantity, so in vector form this will be 1 by 2 pi epsilon naught lambda by r n cap. This n cap is the direction of the curved surface area. Okay, and from this formula we can say that the electric field due to this long straight charge wires is inversely proportional to 1 by r. Okay, so now we are going to understand the electric field due to uniformly charged plane sheet with the help of Gauss law. Okay, so let's this is uniformly charged infinite plane sheets, and due to this charged infinite plane sheet we have to find out the electric field. Okay, with the help of Gauss law. So let this small area whose area is A, and we have to find out the electric flux due to this small area. Okay, so the electric field due to this small area will be phi 1 plus phi 2, because this due to this small area the electric flux towards the left side will be phi 1, and towards right side will be phi 2. Okay, but here you can see that the direction of electric field and surface area towards the left side is same, and also the direction of electric field and surface area towards the right side will be same. So the angle between area and electric field will be 0 degree. So here we can see that we can write phi 1 is equal to Ea cos 0 degree, and phi 2 is equal to Ea cos 0 degree. Okay, so the total electric flux due to this small area will be 2 Ea. Okay, but according to Gauss law, the electric flux is equal to Q by epsilon naught, and here let the surface charge density is sigma. So here you can we can write the charge enclosed by this area will be Q by sigma A, because sigma is equal to Q by A, so Q is equal to sigma A. Okay, and if we put this Q is equal to sigma A in this formula, then we get phi total is equal to sigma A by epsilon naught. And here you can see that from equation 1 and 2 the total flux, this is also total flux, and this is also total flux. So we can say the RHS of this equation and RHS of this equation will be equal. So here you can write E2EA is equal to sigma A by epsilon naught. A to A cancel out, so E is equal to sigma by 2 epsilon naught, and in vector form sigma by 2 epsilon naught n cap. So we can say that the electric field due to uniformly charged infinite plane sheet is equal to sigma by 2 epsilon naught at any point. Okay, from the infinite plane sheet, and here we can say that the electric field due to uniformly charged plane sheet is not depends upon the distance. Okay, it's only depends upon the surface charge density. Okay, and if there is a question to find out the electric field due to uniformly charged infinite thin plane sheet, if this is question is a thin plane sheet, then you have to remember that the electric field will be sigma by epsilon naught. Today we are going to understand electric field due to uniformly charged thin spherical shell. Okay, and here you can see that this is the thin spherical shell whose radius is r, and if the charge is present inside the shell, then it will present on the surface, because inside the surface there will be repulsion between the charge, and as a result they tends to moves as far distance as possible from each other. Okay, that's why they are resides on the surface. Okay, there is no real charge present inside the cell, as you can see in the figure. So here we are going to find out the electric field outside the cell, on the surface of the cell, and inside the cell. And here I use the electric two formula of electric flux, that is electric field into surface area, and also we know that the electric flux is equal to Q by epsilon naught according to Gauss law. So they will be equal, and as a result we get a formula for the electric field outside is equal to 1 by 4 pi epsilon naught Q by r dash square. Here r dash is the distance between the center of the spherical cell to this point P, and on the surface of the cell there are two formulas of electric field. One is 1 by 4 pi epsilon naught Q by r square. Here r is the distance from the center to the spherical cell surface, and if we use in place of Q sigma into 4 pi r square, let the surface charge density of this surface is sigma, so the charge is equal to sigma into 4 pi r square. If you use in place of this Q sigma by sigma into 4 pi r square, then we get E is equal to sigma by epsilon naught. This formula is very important formula, and from this formula we can say that the electric field on the surface of the spherical cell does not depends on its shape of the spherical cell. Okay, and electric field inside the cell is equal to 0 because there is no charge inside the cell. And if you use this formula for this Gaussian surface, then there will be in place of Q there will be 0, so E will be 0. So you have to remember it. Electric field inside the cell is equal to 0, and on the surface of the cell sigma by epsilon naught, and outside the surface of the cell this is 1 by 4 pi epsilon naught Q by r1 r dash.